Work and energy problem solving. A lot of problems in this unit. We're going to start over here on the left side, moving a box, a block and a loop, graphical analysis, block loop and a spring block and an incline plane and a spring marble launcher. Move over here, we have some projectile motion problems. A traveling box, the spring and roller coaster, a sled, a roller coaster, then spring constant of a marble launcher, and finally ramp and a spring. Sled. A student pushes a 10-kilogram sled at a constant speed by applying a force of 75 newtons at an angle of 30 degrees with respect to the horizontal. The sled is pushed over a distance of 15 meters. A. Draw a free body diagram and show all the forces on the sled. B. How much work is done by the applied force F? C. How much work is done by the normal force? D. How much work is done by the gravitational force? E. How much work is done by the friction force? F. What is the coefficient of kinetic friction between the sled and the surface? And finally, G. How much work is done by the net force on the sled? A. Draw a free body diagram and show all the forces on the sled. Draw the forces, but do not resolve them into their X and Y components. The College Board AP exam typically gives a point for each correct force, but will deduct points for drawn forces that don't exist. So we'll start by drawing arbitrary lengths for the friction force, which is opposite the motion, and mg, which is down. Next, draw the normal force, which will be equal in length to the sum of mg and the y component of F. All right, F is going to be like this. It will have an x component and also a y component. Then draw the friction force equal in length to the x component of F, since the sum of the forces in the x direction are 0, as the sled is moving with a constant velocity. The lengths of the vectors don't have to be exact, but should indicate that the sums of the vectors in the x and the y direction are 0. Draw the force and its extension on an xy axis. So the force is here because you're pushing it, but forces always have to start on the actual object right here, this dot here. So it goes in this direction. So the angle, theta, that F makes with the positive x-axis is the same as the angle that the student is pushing the sled, and that's due to a little geometry here, vertical angles. Next, resolve the applied force into its x and y components. Only the x component will contribute to the work done by F, as it is in the direction of the sled's motion. Use trigonometry to find the components. We do this up here. We keep an extra sig fig as this is an interim result. Then use the work equation. Work is F parallel times delta x, or F sub x times delta x. Substitute in our values, and we get 974 joules, and we rounded that to 3 sig figs. C. How much work is done by the normal force? Refer to the free body diagram. The normal force is perpendicular to the motion of the sled, so 0 work is done by the normal force on the sled. How much work is done by the gravitational force? Once again, refer to the free body diagram. The gravitational force, mg, is perpendicular to the motion of the sled. Here's the sled's motion. So 0 work is done by the force on the sled. How much work is done by the friction force? Use Newton's second law in the x direction. The sum of the forces in the x direction equals 0 as the sled moves with a constant velocity. That will find the friction force and then use the work equation. So here's our component of the applied force in the x direction. So the sum of the forces is going to be F cosine theta plus the friction force equals ma, which then equals 0 as the acceleration is 0. So our friction force here is negative, which makes sense because it's opposing the motion. Here's our work equation. It's going to be the friction force times delta x, and again there's that minus sign. So that's F cosine theta times delta x, the displacement. and we get a negative 974 joules. The work is negative as it opposes the sled's motion. An alternate method, and quicker, is realizing that the friction force is equal and opposite to the x component of the applied force F, since the sled is moving at a constant velocity, like we said on the previous slide. Constant velocity shows that the acceleration is 0, so the net force in the x direction is also 0. Since the x component of the applied force was calculated in part B of this problem, it can be stated that the work done by the friction force is also equal and opposite to the work done by the x component of the applied force, so all we have to do is put a negative in front of that 974 joules. What is the coefficient of kinetic friction between the sled and the surface? This time we're going to sum the forces in the y direction to find normal force and then find the friction force. So the sum of the forces in the y direction are the normal, in the up direction, so that's positive, mg is down, so that's negative, and f sine theta is also down, so that's negative. That will equal ma sub y, and that's equal to 0 as the sled isn't moving up and down. So here's our normal force, mg plus f sine theta. Now use the friction force equation, where the friction force is equal to f cosine theta, and rearrange to solve for the coefficient of friction. So here's our friction force, and it's mu k times the normal that we found on the previous slide. Now rearrange this first equation here and get mu k is the friction force over the normal force. Here's our friction force, here's the normal force, substitute in our values, and get mu k is equal to 0.47. How much work is done by the net force on the sled? Well, the net work done in the y direction is 0 for two reasons. F sub y, mg, and the normal force all act perpendicular to the sled's motion. Also, the sled does not move in the y direction. In the x direction, the net force is equal to F sub x minus the friction force. The sled is moving at a constant velocity, which indicates that its acceleration is 0. Since the acceleration is 0, the net force is 0, and the net work done is 0.